I'm about to show you a solution, the best you've ever seen. This is 2925 maximum score after applying operations on a tree. Okay, so there's an undirected tree with n nodes labeled from 0 to n minus 1, okay, and rooted at node 0. All right, so this is a rooted tree. It's an important caveat, right? So it's a rooted tree at 0, and it's undirected. All right, 2 simple points. And you're given a 2D integer array edges, length n minus 1, right, because it's a tree, so there's no cycle, so there can be at most n minus 1 edges. Not an important real caveat about this problem, but just, good common knowledge to know about trees. Indicates that there is an edge between nodes AI and BI on the tree, right? So if you have this tree and you have a node A, and you have a node B, and you have a node C, if you're given A, B, that means that there's a connection between A and B. Notice there's no directionality to this connection. Now, of course, it can be kind of hard to represent this connection programmatically, so usually what we do to represent an undirected edge is to create a link from A to B and a link from B to A, right? Because undirected means that you can go from A to B or from B to A, right? There's no directionality to it, and it's easier to represent it in this fashion, right? But hopefully, if you're approaching a medium problem about graphs, these kind of fundamental ideas are familiar to you. All right, there's an edge between nodes I and BI. You're also given a 0 indexed integer array values of length n, where values of I is the value associated with the ith node. Okay, so not to get confused with the index of the node, right? Because you have nodes labeled from 0 to 1, n to minus 1, but that's not the value of the node, right? That's just the label of the node, right? So the value of the node is different than the label of the node. And that'll become clear when we do a practice problem in a moment. Okay, you start with a score of 0, all right? And in one operation, you can pick any node, add values I to your score, set values I to 0. Okay, now, when I first read this, maybe this is a personal thing, I wasn't sure, like, do I have to do all 3 of these things? Or can I decide to pick the value of I and add to my score? Do I have to? But the point here, excuse my rambling, is that you have to do all 3 of these things, right? So I pick a node, I set the value, I add the value of that node to my score, and then I set the value of that node to 0, right? So pick the node, set the value, add the value, set the value to 0. A tree is healthy if the sum of values on the path from the root to any leaf node is different than 0. Don't know who wrote this problem, but it's a weird way of saying it. But a tree is healthy if the sum of the values on a path from the root to any leaf node is different than 0. So, let's unpack this and think about this in different terms, right? When it's saying that a tree is healthy if the sum of any path, right? So when you have a general tree, right, if we're saying it's rooted at 0, right, you're going to have some system of paths, through this tree. Now, it's not necessarily like a binary tree or something, right? But this is a random example, but I'm trying to make a general case, from this random example. It's healthy if the sum of the values on the path from the root to any leaf node is different than 0. So what does that mean? Well, that means that, if I do any path, right, the sum of this and the sum of this and the sum of this can't be 0. So that means that at least one of the values, right, on this path are non-zero, right? For example, this would be valid, right? If I made this 1, 0, or 1, 1, 2, 0, 0, 0. Why? Because there's a sum that's at least 1, right? Everything else can be 0, but one of the values has to be at least 1 on the path, right? And you also notice that there's this kind of, so that's one way of looking at it. That's one correct, I guess, version. But what is also correct is you can technically make this thing a 1, right? The intersection of these paths also works, right? The intersection. So if I make this value a 1 here, I can actually set everything else to 0. because technically speaking, right, there's this path from root to leaf, right? Root to leaf means from 0 to a node where there's nowhere else you can go, right? This is kind of like the bottom, right? There's nowhere from 1 I can go, right? From 1 to 0, well, there's a sum of 1. From this path here, sum of 1. And this path here, a sum of 1. So that's a kind of like a caveat to think about, right? If you had a situation where, you know, you had this thing going down and then maybe it branched out, well, you know, you can kind of get a 2-for-1 deal. And what I mean by that is if you set this value to 1, right, it works for both of these paths, right? Even though these paths like break up, you still, if you set this center value to 1, it'll help you manage kind of 2 paths being healthy, right? So healthy, we wanted to rephrase this, right? What does healthy mean? Healthy, and why I'm rephrasing it like this will be clear in a second, right? What healthy really is equivalent to is at least 1 node non-zero on every root to leaf path, right? But it could be the root itself, right? Here in this example, it's not the root, right? But here it could actually just be this root, and these are all sum of 1, so it's technically healthy, right? So it's just another way of stating the same thing, right? If the sum is non-zero, then one of the values has to be non-zero, and that's all this is showing here. Why I'm doing that will make sense in a second. Okay, so we want to return the maximum score you can obtain after performing these operations on the tree any number of times so that it remains healthy. So we want to maximize our score, right? So we want to do these operations here and maximize our total score. So that's why we want to just make, and we want to keep it healthy. So what that means is, you know, we want to pull as much information out of the tree as possible, right? We want to pull as many values out as possible. And if we can just ensure that every path just has one value, right? If every path just has one value that's non-zero, then we can pull everything else out, right? Because every time we pull a value out, right, we add it to our score, we have to set it to 0, right? So we have to make sure that we pull everything out, but we also have to ensure that we don't pull out everything, right? We just pull out as much as we can to maximize our score, but we have to leave, you know, a couple nodes here and there to ensure that all the paths are right? So we're kind of like playing this fine little fragile game, right? Because we're trying to pull out values out of our tree, but we have to ensure that it stays healthy. So I'm trying to pull out as much as possible, but ensuring that each path from the root to the leaf is healthy. Kombucha. I quit drinking soda, and I'm having a lot of trouble. Okay, so this example is good, but not as good as this next one. So let's look at this next one. Now, remember I was saying that these are the labels of the nodes, but not their values, right? The values are here. So don't think, oh, this node has value 0, and this node has value 2, right? That would be a simple, understandable, but silly mistake to make in an interview, right? So ensure that you fully understand the example, because then you'll solve a different problem that maybe the interviewer say, why is the output 40? I don't know. I thought it was, you know. So just ensure that you really understand what you're looking at, right? So take the problem slow. Take a deep breath. Okay. So let's draw out this tree here. So I think it's just a bit of a better example. So 0, 2, 1, 6, 5, 3, 4. All right, and then let's label these things with their value. I'm just going to put the value in a different color on the side. So 0 has value 20, 1 has value 10, 2 has value 9, 3 has value 7, 4 has value 4, 5 has value 3, and 6 has value 5. That's super confusing. So always ensure that what you're doing is right. So 0, 20, so 20, 10, 9, 7, 4, 3, 5. Okay. So it's saying that we should choose nodes 0, 2, 3, and 4. Right? So that is the answer. Right? So you take this thing and you're going to choose nodes 0, 2, 3, and 4. And you're going to notice that the resulting tree is, you know, what I was kind of stating about how just have it, you need at least just have one node in the path, right? That's non-zero, right? So 0, 2, 3, and 4. Okay, so if we choose 0, 2, 3, and 4, we get this value 20 right here. 2, we get this value 9. 3, we get this value 7. And 4, we get this value 4. So that's 29, 36, 40. All right, answer 40. You add this up, you get 40. And what does that resulting tree look like? Well, now this has value 0. This has value 0. Right? 7 and 4. 7 and 4. All have value 0. Right, so we basically zeroed these out. And what you'll notice now is that for any path, right, there's one node, right, that's non-zero, right? Because, you know, another way of thinking about this, right, is if you had a path like this, right, for example, and this value was non-zero and this value was non-zero, well, you might as well just take one of them, right? You might as well take one of them because the path is non-zero. If there's two things that are non-zero, the sum of them is non-zero. Might as well just take one away, and that one will also be, it'll still be non-zero, right? So if I have this path, I might as well keep the x or keep the y and zero it out so I can get that plus y out of the equation. Okay. So that's another kind of general thing to think about. Right now, do you take x or do you take y? That's going to be a nice topic of conversation, right? But that's what's happening here, right? This really is just trying to do as much as you can to keep it healthy. So to keep it healthy as much as you can, well, take everything you can until you have to leave at least one thing to make this path good, right? Because if you look at all these paths now, right, although these are 0, this one equivalates to 5 because there's a non-zero thing in the path. This one equivalates to 3 because there's a non-zero thing in the path. This one equivalates to, I guess, 10 because there's a non-zero thing in the path. And this one equivalates to 10 because there's a non-zero thing in the path. All right, so what should we leave in the path, right? We've kind of discovered just by looking at this example and thinking through it kind of intuitively that we're going to leave everything but one thing in the path, right? So which one should we leave in the path? We should leave the minimum. Do we really not take one? Seems so weird to me. Why is this 40 and not 0, 2, 3, and 4? Oh, because I'm making the mistake again of assuming that this is the value 3 plus 4, 7. I'm an idiot, right? I did it again, right? This value is not 3 and 4. This value is 7 and 4, which is greater than that, and that'll make sense in a second, right? We should leave the minimum value for each path. Sort of. And what I mean by that is, like, you know, if we're looking at this situation, right? Imagine we just had a super simple example like this. And this had value 10, 1, 24, 5. Well, I'm going to have to make this, you know, all I have to do is leave one to make this valid, and I want to maximize my score. So which one should I leave? Well, obviously, I should leave the thing that gives me the least amount of stuff because I'm trying to maximize my score, right? I'm trying to keep this situation clean in terms of having a healthy value, something greater than 0. So I can't take everything. So I might as well take as much as I can that'll maximize my score. So I'm going to take this 10, right? I'm going to say, ooh, that 10 is mine, son. And I'm going to take this 24, and I'm going to take this 5. And I'm going to leave this 1 alone, right? Because that way I can get my 10 plus 24 plus 5, right? If I took the 1, then I'd have to swap out one of these things and it'll only make my score smaller, right? So I should leave the smallest thing in the system, right? Now there is a caveat to that, right? And the caveat is, well, you know, if we applied that logic here, right, it might not equivalate to the same thing. And why is that? So, you know, the smallest thing on this path would be this 4, right? And the smallest thing on this path would be this 7. and the smallest thing on this path. So if we go through all of them, right? The smallest would be this 4, this 7, this 3, and this 5, right? So all the leaves have the smallest value, but that's not actually the ones that you take, right? Why did we decide to take the, why did we decide to take the 2 instead of the 5 and the 3? Wait. I'm confusing myself now. The thing we want to leave is the smallest thing on the path, right? So we want to leave the smallest thing on the path. The smallest thing on the path is here, 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 and here, right? So that means we would add up all of these values here, and that would give us 39, right? So if we did the logic of saying the only thing we're going to keep, right, is the smallest thing on the path, right? That's pretty much what this is here. I'm saying, okay, this is the smallest value, so that's what I'm going to keep, right? I'm going to keep the smallest value on the path because that's going to maximize my score, right? Now, this is a simple case, but what we'll notice over here is, well, if I apply that same logic here, right, I'm going to keep the smallest thing on this path, right? The smallest thing on this path is this 5. The smallest thing on this path is this 3, this 7, this 4. I actually end up getting the score of 39, which is less than my ideal 40. Right, so although that makes sense in this kind of skinny one case, there's an exception you have to think about, right? Where you have to think about, well, when is it better or when is it worse? And I guess the best way of explaining this, right, is to say, well, let's say we had the following situation. We had X, okay? And there's a network above it. Let's not think about that right now. And there's a network below it. And there's a network below it here. And we'll say this is value Y and value Z. Okay? Now, in this situation, let's say that Y is the value that this branch thinks it wants to keep non-zero, right? So Y is the smallest value to make sure that the branch is non-zero. Maybe we'll do it like this, actually. Okay. Let's actually do a concrete example. I was thinking about doing a general example, but maybe it's better to just do a concrete example here. All right. Say this is 100, for example. Let's say this is 10. And then let's say this is 5 and 4 and 6 and 7. Or let's do 8 and 9. All right, so this, if we thought about this path individually, right? If it was playing this game, it would say, okay, 8 is the smallest thing on this path here. Man, I'm explaining this terribly. And 6 is the smallest thing on this path here, right? So that's who he would say we want to save, right? But if I save 8 and 6, what does that mean? That means I'm not going to use them. So if I save 8 and 6, then I'm not going to collect 8, 9 plus 6, 15, 14 points. Right? So I'm on this branch going up and I'm saying, this 8 is my best value, right? That's the smallest value. So I should save that on the path, right? That's the one. That's the smallest thing. I should keep it, right? And this 6 is the smallest thing on this path going up. So I should save this 6 because that's the smallest thing on the path, right? When I look at this path and when I look at this path, the 8 and the 6 are the smallest things. So those would be the ones that I save on the path, right? But the truth is, well, if I'm saving this 8 and I'm saving this 6, I'm putting 14, I'm neglecting 14 potential points, right? Now, when we look at this 10, well, this 10, although it's greater than 8 and 6, if I was to save this 10, right? If I was to save this 10, well, then these two paths, I wouldn't have to change the 8 and 6. Now, I would lose 10, but I'd gain 14. In the other situation, I lose 14 and I gain 10, right? So if I do it this way, I get plus, I get the plus 14 and the minus 10. And if I do it the other way, that's the wrong thing I was trying to do here. If I do it the other way, I get, right, if I do it the way where I just try to pick the minimums in the path, right? If I say 8 and 6, well, I'm going to get this 10 now. Or I'm trying to save 8 and 6. God damn it. I'm trying to save 8 and 6. Although I do get to zero out this 10. Right, I get to zero out this 8 and this 6 here. Right, in this example, I get to zero out the 10. But I actually lose the 14 from the 8 and 6. Right, so this puts me -4 down, while this puts me +4. Right, so even though it's not the smallest thing, it's kind of distributed in both paths, right? Since this 10 is it's more special. It's specialer? I don't know. It's more special than this 8 and the 6 because it's shared amongst multiple paths, right? So it's kind of like killing two birds with one stone, right? The idea is, well, since I'm closer to the root and multiple people share this path, right? The total sum of using me as the minimum, right, of using me as the one node that we save will affect multiple paths, right? The reason why this occurs is because when I choose this 8, it's only affecting one path from root to node, right? And when I choose this 6, it's only affecting one path from root to node. But when I choose this 10, that could be the one non-zero value for two paths, right? This has a relationship with two things in this path. It has a relationship with two paths. Therefore, it can service as the non-zero node in both paths so we can use other values, right? So in a more general case, what this basically means, right, is for any node x is going to have a series of children, right? I have no idea how many children. Let's just say generally, right, it has these 3 or more or whatever children, right? We have children 1, children 2, and children 3. And children 3 are both x's too, so they could be expanding out too, right? If x is less than the sum of my children, let's make this better, right? If the value of x, let's just say x is the value. So if x is less than the sum of all my children, right? C1, C2, or whatever, well then, if there's a cost, I don't get, right? If I save the ones in C1, C2, and C3, right? If x is less than that, then I might as well not non-zero out C1, C2, 3, and I should just save this value, right? Even though it's greater than maybe C1, C2, C3, it's still going to be what? It's still going to be a net gain because now all these paths, right? Now I can use everything within this path and everything within this path and everything within this path, right? Because x is now the non-zero component within this pathway, right? So if x is less than all that, then we're going to save x, and that's actually what you return up the chain, right? You return x up the chain. Otherwise, you get x, and you continue with this game of saying, well, I'm going to return the sum of this and this and this, because that's what I'm leaving on the table, right? When I'm pretty much returning to my parent, when I do it this way, is what I'm leaving on the table. And let's walk through this example to think about how that's going to work functionally. All right. So I think we can just kind of summarize here. When we look at a healthy thing, that just means one node on the path is non-zero. That means we only have to save one value on each path. Well, which value should we save? Well, we should always try to think about saving the minimum value, right? But sometimes nodes are shared in multiple paths. Even if that node isn't the minimum, it might result in a net benefit to save that node and take the value of all of the children nodes because that node is shared amongst those paths, right? So even though this 10 is greater than this 8 and 6 alone, if this is the 10 that we use, well, then we can use this 8 and this 9 and this 6 and this 7. Okay. Now, with that said, let's go ahead and do one example to show you kind of how this works functionally. So what we're going to do is we're going to travel all the way down the tree. Now, I'm actually just going to change these things to their values because it's really annoying because we don't even need to know what the... So it's 29, 10, 5, 3, 7, 4. 29, 10, 5, 3, 7, 4. Okay. 29, 10, 5, 3, 7, 4. Is that right? 29, 10, 5, 3, 7, 4. Okay. So what we'll do is we'll think about this in terms of going up the paths and looking at your children and making decisions about what's the better deal here. Okay, so let's just assume that we start left, so we go down, we look at this 5. All right. Now it's only this 5 on this path to save, so I'm going to say I'm going to save this 5. So I'm going to save this 5. So I'm leaving the 5 on the table, so I can't collect that to my score. So my score starts at 0. Okay. Now, before I look at what 9 does, right, I need to know what happens to all the children. So before I process 9, I need to also go down this link and look at 3. And 3 is saying I'm the only value on this path, so I better save myself. So I'm going to return a 3. Okay. And then when I get to this 9, what I'm going to say is, well, I can use this 9, right? And if I use this 9, then I'll get a plus 9 to my score. And I'll have to maintain these current minimums, right? Because if I use this 9, right, the only saved nodes on this path are now this, right? For this path is 9 and 5, 9 and 3. So I have to save these 5 and 3 if I use the 9. If I don't use the 9 and I save it, well, then I don't have to save 5 and 3. But that would give me a score of, that would give me a score of 8. Right, so what I'm really asking here is, well, man, if I use the 5 and 3, right, I get a score of 8. If I leave them on the table and I use this 9, I get a score of 9. So 9 is better than 8, so then I'm going to keep the situation as it was, and I'm going to use this. I'm going to use this 9. When I mean use, I'm saying add it to my score. So I'm going to 0 it out because I know that's the better situation, right? That's the better thing to do here. So I'm going to get plus 9 to my score. And that means that what I'm leaving on the table from this branch is now still 8, right? Because it's this 5 and this 3. That's what I'm leaving on the branch here in this situation, okay? Now I'm back at 20. Now before I can process 20, I have to process all the children. So I look at 10, look at 7. It's the same game here, right? 7's going to say, the best I can do for you is just me, so I have to return 7. Then it looks at 4. 4 says the same exact thing. The best thing I can do for you is 4, so it returns 4. Now here's where it gets interesting, right? So if we're looking at this path, these two paths isolated, right? If I decide to take 10 and add it to my score, I'm leaving 11 points on the board. But if I decide to leave 10 on the board, then I don't have to use 7 and 4. I don't have to leave 7 and 4 on the board because now there's this path and I get a point of 11. So I can either get 11 or 10. If I take 10, I'm leaving 11 on the board. If I take the 11, I'm only leaving 10 on the board, so I get a net benefit of 1. If I instead say, you know what? You're giving me 7 and 4, but really, you're giving me 7 and 4, but it'd be better if I just leave myself on the board, right? I can leave 10 for both of us, and that will actually give us a net benefit of 11. So plus 7 plus 4. And that would mean that I return instead 10 up this branch, right? I return 10 because, well, what I'm leaving on the board is 10, right? I'm leaving 10 on the board. And when this looks at it, it says, okay, if I leave 20 on the board, then I can leave everything below me off the board, right? So that means I could leave this 8 because I've already accounted for what I've taken, right? So I could either take these 8 below, however below they are, right? Here's where it gets a little confusing, but just, you know, kind of believe the dynamic programming aspect of this problem, right? When I go here, I'm saying there's 8 on the board that I left in order to ensure that there's a healthy path going down this link. And here it's saying I left 10 on the board in order to ensure there's a healthy path going down this link. All right, so either I collect an additional 18 by making this green, right? Because I can make this green and then therefore these could all be red. Or I could take this and get an additional 20. So obviously the better thing to do here would be to take the 20, add that to my score, and that's where you get our beautiful 13 plus 7, 20, 20, 40. Right. And then if you go up, you'll notice that this is the right, the same system here, right? Where before I guess I probably should have been better with my convention, right? But it's, you know, red, red, green, 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 red, red. Right? Red, red, green, 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 red, red. Right? So the algorithm really here is say, what do I get if I leave it on the board? What do I get if I take it? Right? If I take it, then I have to use whatever my children decided is the way to keep it healthy. If I don't take it, and I leave it on the board, then I can disregard what my children thought was the best idea. Okay. So here's where it gets kind of good. So let's think about the code. Now, technically, so this is a tree. It's probably 0 to n minus 1. I can tell by the edges, but I'm not going to do that. Let's just make a graph. Now I'm going to disconnect this because it's probably going to increase the processing power of my machine. Okay, so let's just do a default dict. I'm not going to get all fancy on you guys and say, oh, well, technically it could be like this, but this is fine. All right, so default dict, just a list. And then we'll look at each u, v, and g. Now, of course, if you're familiar with any graph problem, this is how you represent, you know, the fact that, you know, these are bidirectional. We just know that it starts at 0 and then you flow down. And since it's a tree, there's no cycle, so we don't have to worry about, you know, weird situations. Like there is a natural root because it's a tree, right? Any value could technically be the root, but we're going to start from 0, and then there's a natural directional component from there, but we don't know what that directional component is, so we just represent it like this, okay? So none of that, what I just said in the rambling makes sense. Just know that when you create trees, this is how you ensure that it's the best way to represent them. Okay. Now, let's have our score. Starts at 0, and then we're going to return our score at the end. All right. Now, let's create a kind of dynamic programming, depth first search, I guess. I don't know what you want to call it. You know, you have your node that you're looking at, and then your parent. We'll set the default to none because, right, since this is directional, we don't want to have like, because technically in our system, there's going to be an edge pointing from 0 to 2 and an edge from 2 pointing to 0. So what we don't want is 0 to go to 2, then 2 to go to 0, and 0 to go to 2. So we'll keep track of the parent. Just know, okay, whoever I came from, I don't go that way, right? Because there's a directionality to this, right? If I go from 0 to 2, I never go back, right? If I go from 2 to 6, I never go back. If I go from 0 to 1, I never go back. If I go 1 to 3, I never go back. Okay. Now, what did I leave on the table? So I'm going to put that left on the table. This is really bad word, you know, terminology, but it's what I've been using during this thing. All right, so I might as well just maintain that. So what I left on the table is whatever was the best decision that I made for all of my children, right? The sum of that, right? What all my children did, what did I leave on the table? Because that's going to be all the things that I'm going to have to maintain. Or that's everything I could get if I leave me on the table. Right, so everything that I left on the table is DFS of V. Now the parent is U for all the V in G of U. Right, so for all the neighbors in U, if V does not equal P, meaning if the child that I'm going to isn't my parent, right? Because technically 2 is going to have the neighbors 0, 5, and 6. But if 0 goes to 2, 2 shouldn't go back to 0, so you just avoid this one. All right. Now, what can we do here? Well, we could say, well, what? All right, so here's where it gets a little tricky. So if the value of me, right, the current node, if you get more by taking me than what's left on the table, right? Meaning, if my value's 10 and all the children saved only equates to 6, well then you might as well take me and then continue that 6 up the system, right? So if my value is greater than what's left on the table, well then you're going to take the current value, which is you. So I'm going to say, okay, I'm going to take the score plus equal value of u, meaning, you know, all my children, they created healthy paths with one value, and it came up with 7 as the total, right? So 7 is what I left on the table. If my value is 10, well, then I might as well take 10 and propagate the 7 up the chain, okay? So self-score plus equal value of u, and then I'm going to return whatever was left on the table, because that's going to be what continues to be left on the table. Now, on the other hand, if my value, right, is less than or equal to, so that's just else, right? But if I'm less than or equal to what's left on the table, meaning that coming up the table, right, like before when you had the 7 and the 4, right, and the 10. 7 and 4 is 11, so that's what you're leaving on the table, and your value is just 10. But if you just leave the 10 on the table, you can take the 7 and the 4, right? So that means I'm going to take the 7 and the 4, right? So I'm going to take what was left on the table, and now I'm going to return the score. No. What am I talking about? Now I'm going to return the value of u, right? Because now I'm deciding, okay, the 7 and the 4, right? I always do this. I always say, I'm going to unplug this because I don't need to explain anymore. And then I'm like, oh, shoot, I actually do need to continue using this as an example, right? What's going on here is my computer's being very slow. Okay, so, right, the 7 and the 4, if I left them on the table, then I'm going to be leaving 11 possible points I could get. So instead, I'm going to take this 10, and then I'll get to collect the 7 and the 4, right? So now 10 is what gets propped up the system, right? So I'm going to prop up this 10 up the system, up the chain. And then at the end, we just return, so we should start at the root of the tree and work our way down. Now, there's going to be some exceptions here when something's 0 or not 0 and all that junk. So we got to think about that, how that's going to work here. Okay, so value of u is not defined, so it's values. Common mistakes made by common fools like myself. Okay. Now that's weird. That's because I messed up my indents. This is all a part of the function. Despicable. Self-score plus equal. Now, there's some edge cases to think about here, I think, because when something's 0 or, you know, if it's 0, then you have to take what you got, right? So greater than or equal to. So if your value is 0, let's think about this. Okay, so it's going to get down to 6. And then 6 is 6 greater than... Well, I'm going to have to leave it on the table, right? So if I'm leaving it on the table... So there has to be something to pull from in order to leave it, right? Because if I'm the only node, and I'm trying to think about the edge case where I'm a single node. Oh, now we're farther from the answer. Okay. So let's get all the way down to 6 here. So we're at 6. What's left on the table is nothing because there's no children. So that's going to be 0. So I have to leave 6 on the table. So left of the table has to be greater than 0. Otherwise, we get no additional score because there's no children, and we return values of u corresponding to, you know, this node that we're leaving on the table. Okay, we go up to 2. We look at 5. 5 is going to be the same game. So then this, so for 2, we should have left on the table 11. Okay, so this is a good way of debugging your code. Okay, so this is really weird, right? Because we're not even getting more than one run. Just one run. What the hell's going on? Good stuff, man. Good stuff. Getting stumped. Well, let's make sure our tree looks good. I'm not solving the same problem right now. That's not a good looking tree. So, oh, for U of V and G, I need to look at all the edges. The simple things in life, you know? All right. All right, and there you go. Probably get the runtime a little bit up if you, sorry, I apologize about that, guys. Just little mistakes, but, you know, that's a good way of troubleshooting. You know, always, every failure is a lesson, right? Make sure that all your systems are set up right? Make sure you're adding all the edges and not adding nothing, and then nothing gets propagated. Okay. So what is the run and space complexity of this problem? Well, it's kind of a confusing one, right? Because we'll just say n is the number of nodes. All right, and m is the number of edges. Well, for space, we could look at, we have to create a graph with all the nodes and edges, right? So we have to look at all the nodes and then all the edges between them, right? So for each node, we look at all the edges. There's 2m edges, I guess, right? But we look at all nodes and edges, so that's m plus m. And then the stack, right? We look at all the children, but we only go down, right? The stack only gets to the depth of the tree, and the tree in the longest place could be all n nodes, right? Imagine you just had a skinny tree. It's like a stick, and all n nodes are just node 1, node 2, node 3, all the way down, right? Where they're just pointing, going all the way down. That would make stack space of n, but that's not going to exceed n plus m. So n plus m space. All right, what about time? Well, we create a graph. We look at all m edges. Right, we look at all m edges, right, in order to append to this tree. And we're assuming that this hash table is constant, right? Amortized constant. And then for this DFS, well, we have to look at all the children, right? But we're going to be exploring all the nodes to try to find out what the minimums are, but we only explore each node once, right? So I look at all I look at all n nodes, right? I look at all of the children of me. I make some decision about that, then return that, and that just goes up the chain, right? But I never look at the same node twice, right? I pull information from a node based on its children, take that, return it to my parent. My parent just considers me one of the child, but that value is pre-populated by me, right? I figure out what the situation is. I figure out what's left on the table, what's optimal, and I return it to my parent, and my parent does the same thing. My parent doesn't have to look at everything below it again, right? I provide it with that information. So I only look at all the nodes once, right? So I had to take m time to add all the edges, and then another n time to actually process this tree, right? Because I look at each thing once. Okay, so it's n plus n time, n plus n space, pretty common, pretty much as good as it gets. And it's just, you know, kind of like a one-pass solution, which is, I guess, kind of cool, right? Because it kind of incorporates both aspects at once. All right, peace out, guys.